Hello. Now, I want to make an introduction, and before jumping into the specific topics of the analysis class, I want to repeat what we learned so far. So, we'll start from the statics. Let's very briefly try to remember what we learned. Our starting point in statics is actually the equation of motion, the very simple equation. Force is equal to mass times acceleration. And this is for a particle. Is a point-like structure, so when you apply a force, it just moves. But when I add another dimension, not a zero-dimensional member, but one-dimensional member, and our dimension has a length, and let's say that this is the center of gravity, and I apply a force like that. So how does it move? So in order to describe that motion, we need a coordinate system. So let's write a coordinate system. Let's say that that's our x, y, a Cartesian coordinate system. And we divide the motion into three components. The first component is translation in x. I mean, we know that in that force it doesn't translate, but I'm just writing a very general term, so it moves this way, so that's the translation, plus translation in y. Let's draw a figure for that. This is the same beam, so it moves in the y direction, so this is the final position of that beam. Plus, of course, we need a rotation. In the rotational motion, we don't have any translation, and the member rotates along the center of gravity, and that's the rotational motion. So basically, with these three components, we can describe any type of motion of a rigid body. Now, how can I write the equilibrium equations, the dynamic equilibrium equations for each case? So for the first case, we say that the sum of forces, all the applied forces in the x direction, is equal to the mass of the body times the acceleration in the x direction. Likewise, in order to figure out the motion in the y, or write the dynamic equilibrium equation, we say that the sum of forces in y direction must be equal to mass times acceleration in y direction. But also we have a rotation. And as you see, if you go back to this force, take a look at that figure right here. This F will create a rotational motion because it's not directly applied to the center of gravity. So we call the rotating effect of any force by moment. So the sum of moment in this element must be equal to the mass moment of inertia multiplied by the rotational or the angular acceleration. So these are the three dynamic equilibrium equations that we can have for a member in two-dimensional space. But in statics, we simplify it because for most of our case, our structures, we don't want our structures to move, right? So we say that under any given applied forces, if we don't want our structure to move, we say that the acceleration must be equal to 0. The translational acceleration plus the angular acceleration. So this is the static condition that we have. We say that no acceleration So by using that, we say that for a system to be in static equilibrium, if we have examining the structure in two-dimensional plane, we must have the total sum of forces anywhere in the structure must be equal to 0. The sum of forces in y direction again must be equal to 0, and these equations must hold anywhere at any point in the structure, and sum of moments must be equal to 0. So this gives us 3 equilibrium equations. So if I have a three-dimensional structure, or if I want to analyze that structure in 3 dimensions, then I will have 3 translational components, sum of forces in x equal to 0, y is equal to 0. So these are all the translational motions, equations related to the translational motions. And we have equations related to the rotating motions. And in 3 dimensions, we have 6 equilibrium equations. And if you think about it, in statics, this is what we do. We had 3 equations and we try to analyze different types of structures. So now let's take a simply supported beam now. And I apply a force at the middle. Let's give some numbers. Let's say that that's 10 kilonewtons. 2 meters. Okay? So when I look at that structure, how many unknowns do I have? That's what we are doing in statics. So, oops, I erased that. Let me add it. So one unknown is this support reaction, because remember that we define a pin support. We say that this point cannot move in the x and y directions, and it's supported by this pin support, and we have 2 reaction forces here. Let's call it A and B here. So I have AX and AY, and here this is a roller support, meaning that it can only resist translation in the vertical direction with the help of a support reaction. Let's call it BY. Okay, so when I look at that structure, I got 3 unknown support reactions. Okay, and this is, we are solving this structure in 2 dimensions, so I got 3 equilibrium equations. And what I learned here is I got 3 unknowns and 3 equilibrium equations. So our conclusion is we can determine all support reactions and internal member forces using equilibrium equations. So we call this type of structures as determinate structures. Why? Because I can determine all the forces by just using the equilibrium equation. So it's determinate. I can determine it, right? But remember, this is of course the mathematical definition or the mechanical definition. Now let's take a look at the behavior. How does a determinate structure behave? Now remember that these are the minimum requirements for stability. What do you understand from the stability? Having 3 support conditions for stability. What will happen if I remove this roller support? How does the structure move? Remember, I don't have enough resistance to avoid motion in this structure. If I remove that support B, it will start to rotate. So this structure will no longer be in static equilibrium. It will move, okay? So the minimum condition for a 2D structure is to have at least 3 unknown support reactions. Okay? So if you don't satisfy this 3 support reaction condition, you have, of course, in terms of statics, we say that your structure loses its stability, it will collapse. The other property of a determinate structure is as follows. Let's say that I have these 3 structures. The first one is I have a very thin member. In the second case, I put a very strong member. And in the third case, let's have a random shape beam here. And again, it's pin supported. And for these 3 cases, I apply the same loading, 10 kilonewtons at the middle. What do I find as my support reaction? In 3 of cases, they are always the same. So the shape, whether it's a metal or a wood, doesn't matter. We always have the same support reactions, right? The same internal forces, because the force distribution depends on equilibrium equations, these 3 equations, nothing else. And if you look at these equations, we don't have the sectional properties. We don't have the material properties in these equations. So actually, the force distribution or the support reactions is determined by these 3 equilibrium equations. Now, let's add another span. Now let's consider a continuous beam. All right, so I have a roller support here, and I add another span, another roller support. So I have 10 kilonewtons here. These are all 2 meters, 2 meters. And let's say that the second span is 4 meters long. Point A, point B, and point C. Now this time, let's take a support reactions. Again, I have AY, AX, BY, and CY. Now, in that case, what do I have? I got 4 unknown support reactions. But the number of equilibrium equations, they don't change because it's a 2-dimensional plane, and in a 2-dimensional plane, we only have 3 equilibrium equations. Right? So by using the 3 equilibrium equations, I cannot determine the unknown support reactions. So our conclusion is, by using equilibrium equations, we cannot determine the unknown support reactions. So if we don't determine the unknown support reactions, or we cannot calculate the internal moments, we cannot calculate the deflections. So this type of structure. We call it indeterminate structures. Right? Because by using the equilibrium equations, we cannot determine all the unknowns. So what do we do? So I need additional equations. Okay? So we need additional equations. So what else do I know about this structure? Now, related to the forces, I have only the equilibrium equations. Now, I'll take a look at the deflections or the deformations. What additional information do I have? Now, I have a pin support here. So the deflection here is equal to 0 in the x and y directions. Likewise, at P, the deflection is equal to 0, and at C, the deflection is equal to 0. So let's sketch the deformed shape. Probably it will deform like that. But the condition here is delta y at B is equal to 0. Delta y at C is equal to 0. Delta y A is equal to 0. So these are the additional informations that I have at this structure. So what do we call these additional information? The information related to the deformations, they are called the compatibility equations. Right? The equations related to the geometry or the deformations of the structure. Equations that describes the deformation of the structure. Okay, now I have this information, that one and that one. And also I have the equilibrium equation. So the question is, how do we combine compatibility equations with equilibrium equations? That's the main question. If we can find a way, we can actually analyze any type of structure, whether it is determinate or indeterminate. But of course, the other thing that I need right now is, how can I describe the deformation of a structure? How does a structure deform? That's the question we are asking ourselves, because we need that information to analyze any type of structure. So that we learn in mechanics of materials. Because in statics, we can only use the equilibrium equations, and we can only analyze determinate structures. And here we saw that in order to analyze an indeterminate structure, we need additional information and information related to the deformation. So how does a structure deform? That's the question we ask in mechanics of materials. How members deform. This is mainly what we focused on. And we try to relate the deformations with the internal forces. But of course, when we say mechanics of materials, it's a very wide topic. We limit it. We say that we only looking at the solids. The other issue is it's only elastic material. And we assume small deformations These are our limitations of our discussion in the mechanics of materials. We'll say these are the limits and basic assumptions. Now, we separate in the behavior of a structure as actions, and we have the effects. So that's the main simplification we have. Okay, we have some actions on a structure and we see the reactions. Now the actions for us are the loadings, right? We have point loads and we classify the loads. We have point loads, we have uniformly distributed loads, we have moments, we have thermal effects, and so on. So these are all external effects. We classify them as our actions. Okay? And when you load a structure, it has a response. The response is as a deformation. That's the approach. You load a structure, you get a response. The response is the deformation. The deformation is something that we can measure, we can visually see. But the deformation is really very complicated for us again. So we simplify it. So we classify the deformation in four sections. The first section is the axial deformation. The second one, these are all the chapters of the mechanics of material. You first examine the axial deformation, and then you examine the torsional deformation. And then flexural or bending deformation. And finally, we examine the shear deformation. Okay? So our approach was as follows. We have an action, a load. So let's take a look at it. Draw a simple figure. I have a load on the structure. So what does it cause, that load? That load causes a moment in the structure. So we draw a moment diagram, right? That's the moment. And because of that moment, internal moment, we see a deformation in the structure. So the internal forces, the stresses due to that internal forces, they are all abstract things. They don't exist. What really exists is the deformation. But we use these internal forces, stresses, to relate the external effects with the deformations, okay? So how do we do that? And in most of our derivation, we take a complex structure. Again, this is our simply supported beam. And then from that element, we take a very small piece. We call it infinitesimal element. Depending whether we are doing a formulation in 1 dimensions or 2 dimensions, the shape of the infinitesimal element change. So we can take an infinitesimal element. Let's exaggerate it. I have an infinitesimal element whose dimensions are, if it's 1 dimensional, it's dx. If it's two dimensions, we have dx and dy, and we have some forces on it. So we no longer call the force on a dx infinitesimal element as force, but we call them stresses. And we have deformation of this infinitesimal element. And again, we don't call them deformation if it's on the infinitesimal element, but we call them strains. And then we try to relate the strains with the stresses and the deformations with the strains, and we do some formulations, and we come up with some equations that relates the applied forces with the deformations. So I will not go into details of these derivations, but let's focus on the types of deformations that we see. Okay, so action and let's show the effect here. Okay. I have this, let's take a square, and I apply an axial force, or you can just take a slice from your member, and what you see is the internal axial force on it. So let's call it N, to imply that that's an internal force. So how did we define the deformation due to axial force? It is by elongation. Initially, this was a square, but due to the applied axial force, now we have a longer member. This is our deformation. If we are writing this on a infinitesimal element, we just use the axial strain. But let's write it in a very general way. This is the axial deformation. Converts squares into rectangles. So that's the way we define the axial deformation. You have an axial force on your member, and the deformation that it causes, the shape change that it causes is as follows. Initially you have a square, and due to the axial deformation, it becomes a rectangle. It elongates. That's the way we describe the axial deformation. Now we can have a flexural deformation. We say that the flexural deformation is caused by internal moment. Okay? Now, how does it deform? If I have a square, what type of a shape will I get after the application of this moment? We say that it will become a trapezoid. Right? Because this moment will try to shorten this top fiber, and we'll have tensile components of this moment. It tries to elongate the bottom fiber, and at the end of the day, we have a flexural deformation that converts squares into trapezoids. Okay, so how did we describe that deformation? In a very simple way. We will go over it later on again, but we say that this will be, not this one, sorry, let me erase that. Oops. Let me redraw it. We just use this angle. That angle tells us how much deformation we get, and we call this angle as phi, and this is the curvature. So we describe the flexural deformation with curvature. We say that the axial force causes axial deformation, moment causes curvature. That's the way we relate the internal forces and the corresponding deformations. We have one more deformation type. We have torsion, but I will not focus on torsion here. Now, this is the internal shear on a member. So what kind of an effect does it cause? So I have a square element here. So initially I have a square. So what will happen if it undergoes shear deformation only? It will be, by definition, we say that shear causes angle change. So initially these angles are 90 degrees, but since we have a shear deformation, they no longer become 90 degrees, they change. So shear deformation converts squares into parallelograms. And the way we describe the shear deformation is this angle change, and we call it shear strain. All right, now for an infinitesimal element, we can determine how a force, whether axial, whether moment, changes its shape. But what about the member? And also, what about structures? Yeah, we briefly talked about the members in the strength of material course, but actually that's the topic of the structural analysis course.